and you can tell everybody this is your song. It may be quite simple, but now that it's done, I hope you don't mind, I hope you don't mind that I put down in words how wonderful life is while you're in the world. I sat on the roof and kicked off the moss. Well, a few of the verses, well, they've got me quite cross, but the sun's been quite kind while I wrote this song. It's for people like you that keep it turned on. So excuse me for getting, but these things I do, you see, I've forgotten if they're green or they're blue. Anyway, the thing is, what I really mean, yours are the sweetest eyes I've ever seen. And you can tell everybody this is your song. It may be quite simple, but now that it's done, I hope you don't mind, I hope you don't mind that I put down in words how wonderful life is while you're in the world. I hope you don't mind, I hope you don't mind that I put down in words how wonderful life is while you're in the world. It's a little bit funny, this feeling inside. I'm not one of those who can easily hide.
Hello everyone, good afternoon. I hope you're having a nice day. I am Jean Torres Leite, a PhD student in Genetic and Plant Breeding at Universidade Estadual do Norte Fluminense, Darcy Ribeiro, UENF, and also a member of study groups Ganho Genético and InterGen. At this moment, we start the third and last day of the third InterGen Series, which has the subject Artificial Intelligence in Plant Breeding, New Approaches to the Challenges of Climate Change. This symposium is promoted in partnership with the Corteva AgriScience. First of all, we would like to thank our sponsors and supporters, Corteva AgriScience, Infoline, Broadband, Rio Norte Sementes, and ConnectaGen Group. To the participant, thank you for your time and for choosing to participate in our symposium. Before we start with the lectures, let's get to know a little more about the InterGen Group.
The Brazilian territory has a large area, housing several biomes which directly impact the country's agriculture. The challenge of meeting the growing demand for food in the world has led to the advancement of research in genetics and plant breeding, which enables the increase in productivity and the adaptation of different cultures to different environments. For decades, many universities have been working on the development and the improvement of different species of agronomic importance, in addition to training professionals in the area. Considering the current demand of agriculture, young researchers in genetics and plant breeding not only need the technical knowledge learned and developed at the universities, it is also necessary to go beyond the research itself and seek as much information as possible through the exchange of experiences with professionals and students from different Brazilian regions. Thinking about these needs, InterGen was born. InterGen is an extension group in genetics and plant breeding, aiming to bring graduate students closer to plant breeding in Brazil. In addition to this main objective, the group promotes science through annual symposiums and meetings to integrate the groups and to contact researchers in the field of plant breeding. The InterGen Group is also part of a network called the Plant Sciences Symposia Series, promoted by Corteva AgriScience. In this project, organized by several institutions around the world, students are encouraged to organize scientific events that promote discussion between the academic community and industry. Currently, InterGen is made up of 7 groups from different Brazilian states: InterGen from the Universidade Federal de Goiás, Gen from the Universidade Federal de Lavras, and the Gen Melhor from the Universidade Federal de Viçosa, representing the state of Minas Gerais. GEMP from the Universidade Estadual Paulista, Júlio de Mesquita Filho, and GVENC from the Universidade de São Paulo. Ganho Genético of the Universidade Estadual do Norte Fluminense, Darcy Ribeiro, representing Rio de Janeiro, and NewGem of the Universidade Federal do Rio Grande do Sul. The different plant breeding groups that are a part of InterGen are always interacting through the participation and dissemination of various webinars, lectures, workshops, and other events that each group carries out, building a support network among young researchers. For the next few years, InterGen members will also have mentoring to develop their soft and hard skills, allowing for more effective leadership and contribution to the groups they belong to. If you are a student in the field of plant breeding and want to participate with InterGen, get in touch with your university's group and contact us. We are open to the entry of new groups. And for you, who are a researcher, come be our partner and help us to develop future breeders, strengthening plant breeding in Brazil.
Hello everyone, my name is Rosimara Barbosa Bispo. I am the General Coordinator of InterGen in the 2022 and 2023 Management. I am a part of the study group Ganho Genético at the Universidade Estadual do Norte Fluminense Darcy Ribeiro in the state of Rio de Janeiro. As you already know, InterGen is made of 7 universities from different Brazilian regions, with 2 representatives from each group. So let's get to know the other members.
Hello everyone, my name is Jean Torres Leite. I'm a part of study group Ganho Genético, linked to the graduate program in genetic and plant breeding at the Universidade Estadual do Norte Fluminense Darcy Ribeiro in the Rio de Janeiro state.
Hello everyone, my name is Givanildo Silva. I'm part of the group Roland Vinkovski, linked to the graduate program in genetics and plant breeding in the Escola Superior de Agricultura Luiz Queiroz in the University of São Paulo.
Hello everyone, my name is Gabriel Salgado. I'm part of the study group Roland Vinkovski, linked to graduate program Genetics and Plant Breeding, Escola Superior de Agricultura Luiz Queiroz, Universidade de São Paulo.
Hello everyone, my name is Jaqueline Flores Schmitz. I'm part of study group NewGen linked to the graduate program in Plant Science Crop Breeding at Universidade Federal do Rio Grande do Sul from the state of Rio Grande do Sul.
Hello everyone, my name is Jessica Argenta. I'm part of study group InterGen linked to the graduate program in Plant Science Crop Breeding at Universidade Federal do Rio Grande do Sul from the state of Rio Grande do Sul.
Hi everyone, my name is Bruna de Figueiredo Duarte. I'm part of the study group J Melhor, linked to the graduate program in Genetics and Plant Breeding at the Universidade Federal de Viçosa in the state of Minas Gerais.
Hello everyone, my name is João Marcos Soares Ferreira. I am part of the J Melhor study group in Genetics and Plant Breeding at the Federal University of Viçosa in the stages of Minas Gerais.
Hello everyone, my name is Leonardo Oliveira Silva da Costa. I'm part of the study group GEM, linked to the graduate program in Genetics and Plant Breeding, Universidade Federal de Lagos, Minas Gerais.
Hello everyone, my name is Loriana Gabriela Coelho de Queiroz. I'm part of the study group GEM, linked to the graduate program in Genetics and Plant Breeding, Universidade Federal de Lagos, Minas Gerais.
Hello everyone, my name is Luiz Gabriel Silva Varenga, and I'm part of the study group EUGEN, linked to the graduate program in Genetics, Plant Breeding and Conservation of Plants from Universidade Federal de Goiás in the state of Goiás.
Hi everyone, my name is Giovanna Rodrigues Neves. I am part of EUGEN group, linked to Genetic and Plant Breeding graduated group at Universidade Federal de Goiás in the state of Goiás.
So guys, to start the specific subject of the day, entitled Multiomics Analysis in Plant Breeding Solutions to Complex Plant Breeding Issues, we invited Dr. Juan Diego Hernandez Yarquin from the University of Florida. Thank you very much, Dr. Juan, for accepting our invitation. It's a pleasure to have you here with us.
Hi.
So, Dr. Juan Diego Yarquin works with integration and application of artificial intelligence and omics in plant breeding, quantitative genetics, genomics prediction, statistical model development for agricultural sciences, statistical computing, multi-type and high-throughput phenotype computing, and statistical genetics, Bayesian statistics, spatial statistics, variable selection, and environmental science. Before I give the floor to Dr. Juan, I would like to inform you that the questions and doubts about the lectures can be asked through the YouTube chat. The question will be answered to speakers at the final of the event in the round table. So, Dr. Juan, the audience is yours.
Hi, everybody. Can you hear me?
Yes.
Hi. Thank you so much for this invitation. I feel highly honored being here. I will try to move smoothly with this topic that can be sometimes a little complicated. So I will try to share my screen.
Okay.
Okay, where is it? Okay, I don't know. Oops, it's sharing. Okay, can you see my screen? Oh, not yet. Okay.
Not yet.
Now?
Yes.
Okay.
Can you put in the full screen, please?
Yes, just a second. Okay, can you see the screen?
Yes.
Full screen?
Yes, but it's in the present. I think it's this presenting the
a different screen.
Yes, I think the presenter. I think the model is in presenter model.
Oops.
and we can see your notes.
Okay. You don't have to move this to the. Yeah, I'm sorry, I'm using a different computer. So
Okay.
it's- stop sharing this.
Okay, you have time. No problem.
Yes, no pressure. I think yes, entire screen. I think yes. Oops.
Previous presentations.
I think we close it.
You already closed it. Can you see?
Can you see?
Yes. Can you put in the full screen, please?
I'm not going to have the same problem.
Yes.
Yes, it's the same.
It's the same.
Just a moment.
Oh yes. Oh, perfect.
How about that?
Not yet.
Oh, not yet.
I think we have to.
Oh, can you put in full screen again?
Okay. Now.
Oh, yes, it's working.
Perfect. Thank you so much.
Okay.
Okay.
You're welcome.
I'm so sorry for the for
No
what
problem.
happened. I'm visiting a SIAT in Colombia, and my computer was not able to connect properly to the internet. So I asked a favor. It's okay. Sorry for the delay. I will start now. Again, thank you so much for this invitation. Obrigado, as you guys will say. I feel highly honored being here. And today I'm going to talk about integration of multiomics data using AI methods for plant breeding applications. And then we will discuss some limitations and opportunities. So the outline of this presentation is very quickly. Now we have less time. I'm going to talk about the breeder's labor. So to understand a little more about the motivation, why we are doing these things. And then I'm going to introduce very quickly two key concepts that we consider in plant breeding: genomic selection and genotype by environment interaction. Then we will review very quickly some of the prediction methods and models that were already implemented or developed under parametric approach, and then we will try to understand how these were evolved or how these are connected with the AI methods that we have nowadays, or some of them actually. Then I'm going to show some of the results that we can find in the literature, why these models can be good but haven't shown the real potential. And then I'm going to show some of the new models that we are trying to develop, where we are trying to connect both types, the best, I would say, of both approaches, from AI and from the parametric models. And then with a sparse classification with multi-type data problem. And then at the end, we will have probably this evening time for the questions. Okay, quickly, what's the motivation? What moves us to work in this area? As we know, we live in a world is growing, so we have around 10 billion people expected to be in 2050. Currently, we are around 8 billion people. So one of the biggest challenges of the humanity is to ensure the current and future food supply chains of a growing population. And this is not the only problem. The other problem is that we live in a world that is facing more often and more extreme environmental variations. In this case, the breeders have a main role to develop improved varieties. And we can think of improved varieties of having varieties that yield more, or they are more resistant to biotic and abiotic stresses, etc. So very quickly, this is the conventional breeding pipeline. You know for sure better than I do how it works. At beginning, we need to screen a very large number of genotypes to be able to, I'm going to show my point. Okay, sorry. To be able to select the best ones and increase reduce the number of genotypes to be screened. On the other side, we increase the number of locations where we are testing these genotypes. In a way, at the very end, when we are developing a commercial line, very few genotypes are tested in a large number of environmental conditions or environments. In a way that we are lucky, we will be able to select between 3 to 5 lines that will be commercialized as elite varieties. One of the interesting things, at least in common crops like soybean, soybean pretty much, is that the genetics that we have at the beginning of the breeding pipeline is exactly the same the genetics that we have at the end of the breeding pipeline. In a way that if we were able to develop a method that could help us to find what the reduced set of genotypes that we should consider to advance in the breeding pipeline at the very early stages, we will be able to save the most important resource, time. So also money, also resources, land, water, etc. Okay, some of the inconveniences of this conventional breeding pipeline is that we have limited resources, availability, land, and it's expensive, time consuming, so we cannot wait 8 years to, we have to for now, but it would be great not to have to wait 8 years to release a variety. However, in our favor, we have some factors that can help us. We have better sequencing technologies. We can characterize genotypes in better way. We have better ways to characterize environments using environmental conditions. Also, we have the help now from automated system that can help us to capture a wide range of phenotypes using high-throughput phenotyping methods. And also, we have improved prediction models. We have the parametric and the non-parametric sides. We have artificial intelligence, we have machine learning, deep learning, FDR boosting, and hybrid methods that can be combined. Can be obtained by the combination of these two. Okay, why we are talking about these things? Because we are trying to save time, pretty much, in order to select the genotypes to be advanced. So, as we know, many of the important traits are complex in the sense they are affected by a large number of small gene effects, and also these gene effects are affected by the environmental conditions that they face in fields. In a way, these two factors interact in many complex ways. Suppose that we have a set of genotypes tested under normal conditions, but let's say that at the same time or later on, this same set of genotypes is tested in challenging environmental conditions. It might be the case that some of these genotypes will be able to make it through these challenging environmental conditions. So the idea is trying to develop methods that can help us to anticipate what could be the set of genotypes to use when we can experience negative environmental conditions or challenging environmental conditions. For this, we have tools like genomic prediction. It's not an emerging methodology anymore. It has been tested in many different crops and have shown that actually some genetic improvements can be obtained. So the concept is very easy to understand. Initially, we need phenotypic and genomic data to train the models, and then we can use this information to evaluate test candidates using their marker profiles in a way that we can provide these predicted values as surrogates of phenotypes to the breeders, and the breeders in theory might want to look at the values in order to help with the selection process. Again, the breeders are interested in developing genotypes that perform others in a wide set of environmental conditions, and for the reason they have to test genotypes in multiple environments. However, in many cases, we experience this type of behavior where, let's say in this example, we have 3 genotypes tested in 2 environmental conditions, where genotype B has a low performance in a low environment, a high performance in a high environmental value. The opposite for genotype C, and genotype A is constant. If the breeder wants to select the best genotype across the environmental conditions, they won't be able to find the best one in this case. Let's face it, breeders deal with thousands of genotypes tested in multiple environments, not just 2. So in those cases, this problem becomes even more difficult. So we have 3 different options to solve this problem. If we want to solve, we can ignore the fact that we have this effect. It's called genotype by interaction, and we can use select using the means across environments. We can reduce it by selecting for local adaptation, but might not be the most desirable outcome. And then we can exploit it by trying to borrow information between genotypes tested in different environments in a way that we can try to find those genotypes that are stable across environments. Okay, now let's have a quick review of the prediction methods and models. So far we have in one side parametric models, you can say Bayesian or penalized methods. We have non-parametric methods, or what we call hybrid methods. And we found that some of these are generalizations of existing methods, but considering hyperparameters in the case of AI methods. So very briefly, we have two big branches as parametric, where we find penalized and Bayesian methods, non-parametric, where we have kernels, AI, machine learning, deep learning, etc. And some hybrid methods that are based on kernels, where pretty much we are trying to simulate these complex methods from AI. No? Let's say that we are trying to explain the performance of genotypes based on a wide set of data types. Oops, sorry. Sorry. Can you see my screen still? Okay, there. Okay, so we can use a function where we can pretty much relate all of these different sources of variability to explain the phenotypes. Genetics, could be pedigree, could be markers, RNA-seq, and other layers of the omics for genomics, weather, soil, etc. So let's check very quickly the parametric methods. We have that we can explain the performance of one genotype using a linear combination between markers and marker effects, and we can have assumptions in two different ways. We can consider penalized regression methods where we have a trade-off between model complexity and model goodness of fit. So where we are trying to find the argument that minimize this sum, the most the error between predicted and observed values plus a penalty, a condition on the effect of the covariates. We find the solution for this case for the R block, assuming normality, is the x prime x plus lambda, the penalty parameter in this case, inverse x prime, and the residuals around 0. So we call this R block model. On the other hand, we have Bayesian regressions where we use a sum a prior distribution for the effect of the covariates, and we find that the posterior mode is somehow equivalent or very similar in the shape to the solution for the R block. Some of the problems that we find in this case is that we have to invert these matrices. They are high dimensional in many cases, and we have to deal with that. So in this case, this lambda parameter is equivalent to somehow to the ratio of these variance components is helping us to break this singularity by adding some bias in the diagonal of this x prime x matrix. We will see later how this is related with AI. We have alternative parametrizations, and the star model that we are using in many cases is called G-block model, where we are just replacing this linear combination by genomic effect, and we stock all of the genomic effects, and we compute by the moments of this vector. So the covariance of G, the stock vector of genomic effects, equal to x beta, has a covariance given by x prime sigma square beta and expected value of 0, in a way that this characterization of the characterization of this random term is a normal distribution x prime sigma square beta, where G is equal to x prime divided by P. In this case, this is the kinship metric, so covariance structure is going to help us to borrow information between pairs of genotypes, because each entry describes the genomic similarities between pairs of individuals. We find that if we solve this problem, assuming normality for the effect of the markers, we end up with a solution for the posterior mode of the genomic effects given by the identity plus lambda times G inverse minus 1 by the vector of residuals around 0. In this case, we are getting directly the combination. So one of the important things here is that we again have here embedded this lambda parameter, and now we are dealing with the inversion of matrices of order n by n. So this is less challenging than matrices of order p by p, assuming the p is greater than n. Doing research in the same sense, we developed many years ago already a model that allows to include interactions between genotypes and environmental factors via covariance functions. So we developed this reaction norm model that helped to improve predictability. And we consider this interaction component between markers and environmental covariates. And we found that when we characterize this component, the covariance structure is equivalent to the product between the covariance given for kinship metric based on markers of pedigree and the metrics constructed with the environmental values. In that way, this is just the cell-by-cell product between these two covariance structures. Now we just characterize this as a random term that follows a normal distribution centered in zero and covariance given by G Hadamard product omega. Now, regarding the artificial intelligence methods, or what sometimes we call non-parametric, we can think of some of these methods as generalized versions of parametric models. We have linear regressions, we have kernels. In the sense of, in the case of the linear regressions or linear methods, we have the main difference is that these require the optimization of the hyperparameters, while the parametric methods use Bayesian or likelihood methods. We have a prior, for example, for Bayesian. On the other hand, the corresponding AI methods use cross-validation studies to optimize the election of this Shinker's parameter, the regularization parameter, this lambda value. Regarding the covariance structure based on kernels, we have these described similarities between pairs of observations or individuals at the level of the genomics, environments, phenomics, etc. So we can think of elaborated relationships at the level of the covariates that can be modeled considering kernels. We can have distance, functions, transformations, etc. In a way that the ultimate goal is to improve the correlation or the correlation between pairs of entries, or between entries for each one of the different model terms. It could be their genomics, environmics, phenomics, etc. And also we have another set of models, neural networks, with these are generalization. It is a generalization of linear methods where we have embedded multiple regressions. We have latent variables, activation functions, hidden layers, hyperparameters, etc. So here again, when we are thinking about the alternative ways to understand these AI implementations, we have penalized regressions and the Bayesian regressions. And we said that here we can get the lambda parameter given the penalized regressions, or we can obtain also the Bayesian, using the Bayesian approach, indirectly this regularization parameter as the ratio between the variance components of the error and the variance components of the effect of the markers. So we have prior distributions for each one of these ones. So we can get directly or semi-directly this lambda value. So on the other side, we can find lambda using cross-validation studies. So if we are thinking in some similar kind of AI modeling. In those cases, we have it requires to divide the population in 3 non-overlapped data sets, where we use one for compute the marker effects or the effect of the different factors. We have another training set that we are trying to optimize this lambda value for a given decay parameter. So that is fixed, is a hyperparameter in this case. On the other side, we have these are just parameters. Here, these are hyperparameters, meaning those are given. And then once we have the beta values, lambda values, we apply this to the testing set in a way that we can evaluate predictability of the model. Now, regarding the machine learning methods, so some of the first thing that I did when I started working in this area was to understand or to learn what are the AI methods. So we found that if you Google this, it says that it is the theory and development of computer system able to perform tasks that normally requires human intelligence, such as visual perception, speech recognition, decision making, and translation between languages. So, but what about machine learning and derived methods? So this is a graphical representation of the AI methods, and embedded in this, we have the machine learning methods. Embedded in this, the neural nets, and embedded in this, we have more and more specific methods. We have deep learning. So this, all of the categories, or all of the different fashion of these methods that we can find in artificial intelligence. So for machine learning, we have the use and development of computer systems that are able to learn. I think that's the key part, and adapt without following explicit instructions by using algorithms and statistical models to analyze and draw inference from patterns in data. So let's learn a little more about these kernel methods. So if we think of why the response can be explained by a function of the data that we might have, the covariates. In this case, let's say that we have genomic data. We can use this data to map individuals based on similarities. So by transforming x using a function k of x. So the first step is the first step consists of computing this transformation, and this is very useful for capturing complex patterns that we cannot identify or are difficult for us to propose. What are those? Sometimes we might have some feelings of what could be those, but when we don't have any idea, we can use these methods, especially when the number of covariates P surpass by far the number of data points available for model fitting. So P greater than N. Also captures different types of interactions. We have epistatics, G by G, G by E, and epistasis by environment. So here we have what are the different type of kernels that we might find in the implementations. We have linear kernels. We have what is the solution, or what the covariance that we are considering in this case is alpha times x prime, and the parameters to optimize alpha, the trace of this divided by n. So we know this model is known as gblob. We have a similar parameterization for finding the epistatic kernel. I just use the Hadamard product between these two matrices. So we already discovered this. And this is the way how we find the parameter we are interested. Gaussian, based on RBF, they use applying a transformation to the metric, where this metric is sometimes, I mean, in this case, is a Euclidean distance between the genomic information between pairs of individuals squared, and we just apply this transformation, and we optimize the parameter by using the median. And these are particular cases of RKH, reproducing kernel hybrid spaces, or support vector regression. Also, we have arcosine. They use a transformation. I want to explain the whole transformation in this case, which is based on sines and cosines to modify the axis. In this case, we optimize by finding the right parameter for theta. So this can be think of a deep kernel of a hybrid method that tries to mimic the deep learning methods from machine learning. So this is the way how we find the solution. Many times we cannot get the solution at once, especially when we have very large number of parameters. So if we think of the linear predictor y equal to g plus e, we have the k is too big to factorize. The solution, I mean, the factorization is null. I mean, we don't have a factorization, and the solution is equivalent to the normal equations, where we have k plus lambda I, g equal to k y. So g is equal to g. Is how we get the prediction of the breeding value. If we can find the inversion, it's going to be very easy just to get the inversion of this k matrix. It's not full rank, it is full rank, for example, or it's not that complicated. So we can just think of getting this, the inverse of this, and again, g is equal to g, Or if we can perform the spectral decomposition, it could be eigenvalue decomposition. For example, we can factorize these metrics in three matrices, two associated with loadings or eigenvectors and one associated with eigenvalues. And we obtain the solution of G as a transformation of U times A. And also using the Cholesky decomposition, where we can factorize this using the upper triangular matrices. They are very easy to get the inverse because we just rely on the diagonal of the matrix. And then we obtain the solution by getting G equal to L, the product of the triangular matrix, by A. Okay, now let's talk about the artificial intelligence methods based on deep learning. So we saw the support vector machine, random forest, deep learning is a set of methods for machine learning for GS, for other implementations also. A deep learning is a subset of the machine learning, which is essentially a neural network with three or more layers, and these neural networks attempt to simulate the behavior of the human brain, albeit far from machines its ability for now. Allowing to learn, that's the key part there, from the large amount of data. So here we have that we can characterize the inputs. We can put here all of the different data types of the information that we have. It could be genomics, phenomics, weather, etc. And we can think of neurons as linear combinations of all these inputs. We also have embedded some kind of activation function that based on some criteria, we can activate whether the neuron is important to contribute to explain the variability or not, and then we can keep moving to the next layer and so on. So we have, in these cases, different parameters that we might be interested in optimize, and each one of the layers we have bias, we have weights, etc. And we have to we have embedded the different regressions. At the end, we use a linear combination of the neurons derived from the last layer to predict the performance of the unobserved genotypes. In this case, we have the machine learning. It have, as we said, learnable structures. We have weights and bias, but also we have structures that are not something that where the method can learn. So these are the hyperparameters. And in this case, we have neurons, hidden layers, number of layers, type of activation function, etc. So since the hyperparameters are provided for the user, many possible scenarios or combinations should be considered to find the best strategy initially. This is a small example. Suppose that we have 8 choices for the number of layers. Could be 3, 4, 5, 6, 9, 10. So there is not a rule that we can find the optimum number of layers before doing the analysis. 3 choices for the number of neurons per layer. It could be 4, 5, 6. 4 choices for activation function to decide whether a neuron has relevant information or not. So the total number of potential scenarios is 3 to the 3, 3 to the 4, 3 to the 5, 3 to the 6, 3 to the 7, 3 to the 8, 3 to the 9, and 3 to the 10 times 4 activation functions. This is a total of 88,560 times 4, around 350,000 combinations. The scenarios that we might consider to find the optimum for one rep, because every single time that we run these methods, we have a random component embedded. So here we can take advantage of the high throughput computing facilities using thousands of cores simultaneously. So we already developed in this paper some methodology, or one methodology that can help us to develop complex pipelines in a very easy way, assemble modulus for conducting predictions using parallel computing for millions of combinations. So tuning process of hyperparameters consider 3 different non-overlapped data sets. We need first one for training the set, for training the learnable parameters, another not overlapped for tuning the hyperparameters, and finally one for testing or validate whether the strategy that we are following with the estimated parameters and the hyperparameters is helping or not in the terms of predictability. So using similar ideas to what we have here, like dividing the three different, dividing the whole population in three different data types, we developed some models where we are trying to combine the best of the AI, the pure B AI, and the best of conventional prediction methods. So we develop an implementation that we can actually improve classification compared with machine learning methods. So we will see this at the end. So these are some of the results available in the literature. So we have the Montesinos et al. Is one of the pioneers in the advancing these models using AI. They tested the models using 9 different data sets, and they compared versus the model that we proposed many years ago in terms of predictability. So these authors found that many cases when interactions were not included in the model, in this case in the right panel, deep learning outperformed conventional GBLOB models. Because as we said before, it has embedded somehow this or can find these complex relationships. However, when the interaction was included in both methods, deep learning and GBLOB using the rational model, the extended GBLOB model outperformed deep learning in most of the cases, in this case in the left panel. So we have here in red the results from the deep learning, in gray the results from the GBLOB. So here is very clear that deep learning is better, here is not that clear. So these results highlight, in this case, the importance of using these AI implementations in order to be able to capture these complex relationships. However, when we are able to formally include these parameters in the model, we don't see that much improvements compared with the conventional AI methods. Also, we recently published in this paper a study where we try to compare the different 4 different methods: GBLOB, Gaussian kernel, deep learning, and ArcCosine kernel, with and without interaction to predict yield performance. We study the case of predicting sparse testing, so genotypes in already genotypes in already environments. So this is what we call CV2. We have in orange the GBLOB model and in gray the deep learning method. So for a direct comparison. So we have when we don't include the main effect, so the interaction between genotypes and environments, deep learning does a good job in some of the environments, but not in others. However, when we include these interactions, it's clear that the methods based on covariance structures outperform the deep learning method. On the other side, we have the predicting new genotypes that we didn't observe in any environments using the main effect method only, or models. We have better results using deep learning. However, when we consider the interaction components, the improvements are not that clear. Actually, the parametric or semi-parametric or hybrid methods do a better job in this case. So pretty much these results highlight the need of developing new improved prediction models under conventional and AI approaches for improving predictability. So here we have there are some advantages of the machine learning methods. Support vector machine and random forest. They are very easy to implement, require very few parameters to be tuned, little time to provide complete predictions. Deep learning is very powerful, capturing complex patterns in the data, like interactions. Also supports raw data, so there is no need to process the data. We have integration of several sources of information, omics, such as pedigree, genomic data, environmental data, metabolomics, microbiomics, phenomics, proteomics, transcriptomics, etc. The downside is that we don't have a strong theoretical support, guaranteed only local minimums, computationally are demanding, requires tuning of hyperparameters. As we saw, we can end up with millions of combinations. Different omics are treated at some point as the same data type, and no interpretable resources might be obtained. So these are these methods are also known as black boxes, which return outputs for a given input. So take-home message is these are very good methods for performing predictions, but we cannot blindly adopt them. Somebody already said in a few publications that these methods are not a panacea. We still have to develop in-house implementations. So now I'm going to switch gears. I'm going to talk a project that we were working for quite long already, and it's almost about to be published, the integration of multiomics for improving phenotype prediction in the binary case. So we tried, again, as we said before, try to take the best of each one of the implementations, AI and parametric methods. So we have the nowadays sophisticated and automated system allow the collection of different types of data with potential applications in plant breeding. We have high throughput sequence and phenotyping, drone, greenhouse data, pictures, etc. The integration of these multiple omics is increasing expectations to improve predictability of current models. However, the large number of covariates also poses challenges for bringing this information in the model. In plant breeding applications, the main problem when combining two data types like SNPs and secondary traits is that the genomic covariates will outcompete the phenotypic covariates to explain the performance of the plant. So you have millions of markers and information on 20 secondary traits, whatever is there goes away with this large number of covariates when you treat them as the same type of variable. So we have data classification problems. We have the several traits can be categorized based on continuous measures. I mean, soybean, we have lodging and shattering, it has categories 1 to 5, draw and salinity tolerance for rice, for example. So the simplest case corresponds to the binary outcomes where we have only two categories, zeros and ones. In this case, we try to leverage the concept of sparsity that is linked to the identification of major genes controlling trait performance. Again, out a large number of genomic variants, a small number is highly correlated with the response. Also, usually secondary traits have a lot of information with respect to the main trait of interest. Like, for example, yield, we can use canopy coverage, lodging, shattering, etc. In this study, our goal was to develop a method that performs conventional Bayesian and machine learning classifiers. Pretty much we tried to blend both of these. So we have Bayesian, lasso, A, B, we have random forest, support vector machine, FDA, etc. So we consider the binary case. Suppose that we have a large set of microscopic variables P, in this case, U, the matrix of markers, and a reduced set of macroscopic variables Q of this, W, the secondary traits. In principle, we can combine, or we can think of combining both sets in one big matrix and treat them as the same type of covariate. Apply the commonly used variable selection methods, lasso, Bayesian lasso, or machine learning classifiers. In our case, we propose a method that is based on the ideas of Huang and Turnbull, where we use an iterative method for selection shrinkage of variables in highly sparse linear regressions. We use the same principle for the selection of variables. We distinguish the nature of both sets. So here we gave first priority to the set of macroscopic variables, the secondary traits, and then conditionally on this, we selected those variables in the microscopic set, so the molecular markers. We call this one-pass method. So this method, how it works is we start selecting for the secondary traits at the point where we cannot increase the likelihood more, and we break the loop. If we have 20 secondary traits, probably we selected 10, and those were enough to explain why. And after that, we started selecting from the set of markers. And then we add a threshold optimization to find the group's memberships, so zeros or one, pretty much, based on the evidence of when is the point where we are going to send predicted values to the group of the ones or the group of the zeros. So we also add another novelty here. We regress the macro variables using the marker data, just one at a time, because we believe that some of the information that is from the secondary trait that is not on the genomic data can be recovered via the residuals. For this, we consider the elastic nets for the regression, the lasso, and the scat. And then we merge the residuals together with this set of genomic covariates. So Again, potentially this will help to recover information not in U, in the macro variable, in the genomic data, but is used in W through the residuals. It's the same principle for selecting variables, but distinguishing the nature of each set. So we are giving priority to the set of macroscopic variables, and then conditionally we select those from the set of micro variables. So we are going to present results using two real data sets. So we have simulations, but we don't like simulations too much. So we have a data set of maize with 277 genotypes, and the main response was tillering, presence or absence of tillering, the extra branches here. There are some maize breeders that believe that when you have extra branches, reduce the yield potential. Other breeders say it doesn't matter. So we just were interested in analyze this data set. So we have information on 20 macro variables or secondary traits, 4 methods to include the macro variables, raw, lasso, scat, and elastic net for the residuals, 5,000 molecular markers, total of 5,020 markers, 420 replicates for composing, training, and tested set. This is the way how we conduct the cross-validation. We use 77 genotypes for testing the model, and for training, we have 200 genotypes. And we divide for one pass method in this way. We have 120 to get the to estimate the coefficients, and 80 to estimate the threshold. And finally, we use this to classify the outcome that we're interested. For machine learning, we use directly the 200 genotypes, and we let the machine learning to optimize in their own way to predict the remaining 77 genotypes. It's the same idea for tuning hyperparameters in deep learning. In this case, we have a given decay parameter for running this optimization. So we evaluate the classification error, so the lowest, the best. So in this case, we have in the left panel the results using the AI implementation, machine learning. On the right side, we have those derived from the methods that we propose. As you can see here, for the different methods that we propose, especially for raw and for elastic net, we have a lower classification error compared with the machine learning methods. So the classification error was significantly reduced by using the proposed methods. However, further developers should be considered to add more omics and multiple categories. Also, we have similar results for the case of soybean, where we try to assign genotypes to different groups, zeros and ones, based on 20 covariates, secondary traits, and markers. In this case, again, we see this clearly, the results with the method we propose are clearly superior when we have different proportions of zeros and ones in the population. We have 50-50. We got classification errors of 0.3 compared with 0.4 with the AI methods. 65-35, we have some cases where we have around 0.27 compared with the 0.35-36 with the AI methods. 75-25%, we can say that they are tied at somehow, but still a little bit of improvement compared with the method that we propose compared with the AI methods. And finally, with the 85-15, I think they are just bailing out the outcome. So we are pretty much getting the same results. So currently, we already extend this methodology to consider the inclusion of 3 different data types: secondary traits, weather, and SNP data. We use a subset of the 3,000 lines of chickpea tested in net environment, 14 million markers, 9 secondary traits, 900 weather covariates. So we have that extended one-pass method returning a classification error only 50%, while the support vector machine and random forest was 30%. So the take-home message is that it's important to treat the different omics differently depending on the nature and number of variants. Adding information of all omics without the previous consideration will not allow us to fully leverage in the prediction classification problems. And the AI methods can be significantly improving by differentiation the different omics, instead adding all this in a bold fashion. With this, I don't have anything else to show. Thank you so much for the opportunity again. Obrigado, and I think I'm open for questions, probably at the end. Thank you so much.
Okay, thank you, Dr. Juan. It was an excellent lecture. So I invite you to join us in the breakout room. So see you late. Okay.
Okay, thank you.
So for the second lecture, I would like to invite Dr. Simon to join us. Hello, Dr. Simon.
Hello, can you hear me?
Yes,
Great.
very well. So Dr. Simon started his career in science as an undergrad at Queen Mary University of London, where he studied genetics with a particular focus on polyploid in plants. In 2012, Simon got his PhD in plant genomics and computational biology at the University of London, UK. He made two postdoc research in the University of Iowa in US from 2012 to 2014 and University of California, Davis from 2014 to 2016. Since 2016 to now, he is research scientist at Corteva AgriScience, focused on genome characterization, germplasm diversity, and predictive analysis. So it's a pleasure to be you here, Dr. Simon. I give you the floor. The audience is yours.
Thank you very much. I'm going to share my screen now, and I'd just like you to confirm that you can see the slides that I have up there.
Okay.
Yes, you can see them?
Yes, I can see.
All right, then. Well, thank you very much for the kind introduction. And also, thank you for the opportunity to present to you all today. It's a pleasure to be here. And my name's Simon, Rennie Byfield. And the subject of my talk is pangenomics and multiomics analyses in plant breeding from an industry perspective. And so what I'm going to do before I get into the details of the talk is really call out that in this case, for this presentation, I'm really a representative for the company that I work for. That's Corteva AgriScience. And I'm going to be presenting a very broad overview of a great many projects that we're doing here at Corteva. And most of the work that you'll see has actually been done by a number of other people. So what I've done is, as we go through the slides, in the bottom right-hand side, you will see the names of the individuals who have been key players in generating the analyses and the data that I'm sharing with you. And again, just to reiterate, this is a very broad overview of some of the projects that we're doing with some specific examples of that research. All right, so let me move on to the next page. So this is just an outline of what I'm going to go through. So I'll give you a little bit of a flavor of who we are as a company, who is Corteva, what do we do, and why are we here. And then there are sort of 4 sections that break out in the talk. And they're really about pangenomics and multiomics with a little bit of slant towards pangenomics and how we think about those subjects at our company and how we use information that we're gleaning from those sorts of analyses to inform our breeding decisions as we move forward. So I'll start off with a discussion on the genomics and the pangenomics era at Corteva. And then I'll move on to discuss pangenome gene synteny and how we're actually using the pangenome to dissect some of the sequence variation and structural variation that we have in our genotypes. And then I'll mention briefly how we relate that to phenotype in order to help us make useful breeding decisions. And then the third phase, I will move on to something called the Deep Genome Project, which is really about expanding the horizons of genomics and layering other omics technologies on top of our pangenome project with the aid really of helping us elucidate functional elements of the genome and also allowing us to target gene editing positions in the genome for breeding purposes. And finally, I'll close out with a little bit about machine learning and how we combine envirome information, phenome information, and genome information to help us make targeted product placement decisions so that productivity for farmers in the field can be maximized. So here's a brief autobiography. I was going to describe to you some of my history, but since we've already been through that, I don't want to dwell on it too long. But I do want to call out that I've been at a number of universities and since then have been working in industry with Corteva as a research scientist. All right, so let's sort of just go over a little bit about Corteva and who we are briefly. This is our mission statement, and it goes like this: to enrich the lives of those who produce and those who consume, in ensuring progress for generations to come. And really, that sort of outlines what we want to do. We want to maintain and secure food security for people via innovation and technology development. And we have many research postings around the world. You can see them here. Our headquarters are in Wilmington, Delaware. We have operations in Europe, Asia, and South America. And I have around 20,000 colleagues in the company, which include 5,000 individuals which work in our R&D company. And now, as you can imagine, 5,000 people is quite a lot. So there's an incredibly diverse collection of individuals, lots of interesting characters, and it's certainly a really nice experience to learn how to work with all these interesting people. And I generally enjoy it very much. So we actually were born out of a merger of Dow AgroScience and DuPont, and became a standalone company in 2019. It's June 1st, 2019. And we're in fact the only major agriculture company that is focused strictly on agriculture. So why do we do what we do? Well, of course, the world is facing plenty of food security challenges due to an increasing population size. And that's coupled with, that presents a challenge, basically, to increase the productivity of our crops across the board, more or less, to account for that increasing population size. And what this equates to, basically, is that over the next 50 years or so, 25 years or so, we have to increase productivity by around 50%, which is a tall order. And so as a company, we're trying to bring new technologies and as much innovation as we can to addressing that problem so that farmers can provide the yields that we need going forward. So part of the key to that problem, or solving that problem as I see it, is this genomic prediction piece, which is to use genomic information to predict the value of a given line or variety, the breeding value. And what we are, the focus of what we do really is to maximize the value of the genome in this prediction piece, which happens at the beginning. Greater
Dr. Simon, can you hear us? Can you hear me? Oh, we have a problem here, guys. We will contact the Dr. Simon. Okay. So, Dr. Simon, can you hear me? So we have We had some problem here, guys, and we will start. He start in a moment, okay? We will contact the Dr. Simon again, and then we will start, okay? So, just a moment.
Hello, I believe I got disconnected there for a second. So, hello, am I back? I got disconnected.
Okay, can you hear me?
I can hear you. Can you hear me?
Okay, yes.
Yeah, sorry, I got disconnected, and so I don't know at what point. So I think I was talking to myself for a while.
No problem. It's happened.
Yeah, I'm sorry about that. My internet must have just, had a little
No
error.
problem.
All
Go
right,
ahead.
so
You can continue.
thank you very much.
Okay.
So, as I was saying, linear models for the purpose of prediction work well when the material that you're predicting on is similar to what you would, what you trained your models on. But as the genotypes and the environments diverge, predictions become more and more difficult. And so what we're doing as a company is, of course, trying to bring in as much information about the genetics, the environment, and the management, and coupling that with machine learning and deep learning techniques to try and address those deficits. And I'll tell you a little bit about that in later on in the talk. Okay, so crucial to this generic prediction piece is, of course, looking at sequence data and understanding what that's telling you. And indeed, that sequence data allows us to perform genetic discovery experiments to identify regions of the genome that might be amenable to gene editing, to improve products that we sell to farmers, and also in the efforts that relate to genomic prediction. Understanding that diversity is crucial. Okay, so first of all, I'm going to, with that brief introduction, I'm going to move on into sort of talk about our pangenomics program. And what I want to do here is contrast that with what you might see in a public setting. So usually, the goal of pangenomics effort in a public setting, in academic world, is usually to maximize the diversity that's sampled in that pangenome effort. And so, cultivars, wild races and land races may be picked for such a project. And, generally curation and identification of that variation is the point of that pangenome project. So to maximize diversity. On the other hand, when you have when you're in a closed breeding system like we are at Corteva, there's a slightly different focus, which is to maximize on utility. And so, for example, in a pangenome collection of 15 Corteva soy lines, we didn't necessarily focus on diversity per se, but rather on utility. And so we have a number of key important lines that are represented in among our pangenome, and they relate to key material that's known to produce good offspring, some information about founders, both from breeding efforts in North America and Brazil, and of course some disease-resistant donors, among others. So that's the key difference. In an industry setting, it's often maximizing utility. In the public, it's typically maximizing diversity. So we have, over the last several years, developed a really robust reference assembly cookbook that I just want to review real quickly. And that involves the use of two really key technologies. One is the PacBio Sequel 2 machine, which produces really KB-sized reads out of that machine. And that's coupled with a BioNano Sapphire machine, which uses sequence tags essentially to tag the genome. And what we're able to do is couple this BioNano map with these PacBio contigs into what's called a hybrid scaffold here. So we know what sequences are going to be tagged in the BioNano map, and we can identify those sequences in these PacBio contigs. And that helps orientate and align those PacBio contigs to give us really contiguous and complete scaffolds. And that has produced, generally over the last few years, very nice results indeed. Now, I mentioned to you that the results are generally very good, but that isn't to say that there aren't still problems and challenges in our pangenomic work. And here's an example of that. This shows a BioNano map here on the bottom, and the PacBio contigs on the top and the hybrid scaffold in the middle. And over the centromeric region of this chromosome, what you find is the repetitive nature of the sequences there mean that the BioNano maps are not rendered very accurately or at all, and you're relying on just contiguous nature of these PacBio sequences, and we can't really use the BioNano map to orientate the contigs on this scaffold. Here's another example from the knob sequence in maize. This is, of course, known to be highly repetitive. Again, we see a similar problem. This BioNano map does not span this region well or at all, and we then rely on PacBio contigs alone. So here's an example of a recent, actually it's from 2020, it's not that recent, but it's a maize 23, an internal inbred maize line from Corteva. And I just want to show you a little bit about what this assembly looks like to really highlight what our platinum assemblies are capable of. There really are very, very few gaps in this assembly at all. It's almost gapless. There are only 12 in total. And what you can see along most of these chromosomes, they're the ones that are all in black here. Not most of them, but some of them at least. There are no gaps. So these are completely fully assembled chromosomes that we're achieving here with our new pangenome cookbook. So what do we do with all that information? Well, typically the first thing we would do is take a look at that pangenome collection and begin to examine structural variation. And this is a diagram here, or a plot, beg your pardon, that details some of that structural variation in a few internal Corteva soy assemblies. We use a system called tag dots, which takes unique 10 kilobase sequences in one of the reference genomes and aligns them to all of the other references, and you get this really nice, these nice patterns that allow you to detect very large structural rearrangements between these genomes. For example, there's a nearly 2 megabase pair inversion here and several large indels present in just this single chromosome. Here's a different example, but from maize this time, and this is a region on chromosome 2, and there are in fact several extremely large inversions in this region in some of our key elite material. We've got an inversion that's 27 megabases in size, and that's large enough, but there's an even larger one which is 75 megabases in size, and we had really no idea that these inversions were there prior to our pangenome efforts. It just goes to highlight the importance of having this information in lines that are directly applicable to your particular breeding efforts. Now, we've taken that knowledge, and what we've done is which has been recently published, is worked on techniques using CRISPR-Cas9 to in fact reinvert this large inversion here, such that these two inbreds are in phase with most of their contemporaries. And what we hope that will allow us to do is to unlock some new allelic combinations in that region. And we're just doing experiments now to find out how that looks. And I can't go into any more details at this time. Here is an example which I like very much, which details a particular Corteva sunflower variety versus a public HARN XRQ assembly. So HARN XRQ is on the x-axis here, and the Corteva assembly is on the y. And again, it uses tag dots to look at the collinearity and position of sequences in those two genome assemblies for several chromosomes. And what you can see is that the material are really very different between the public XRQ and our internal line. And you can see immediately when you're thinking about looking at generating genetic maps and understanding sequence diversity in your material, that if you're relying on assemblies that are from external programs, that they may not be as applicable as you might think. There's plenty of rearrangements and inversions and deletions in this particular example. Okay, so I'm going to move on to from that brief overview of where we're at for pangenomics and talk about, well, what do we actually do with it? And so some of what we do is, of course, look at that structural variation and in particular gene content variation and how you can use that to essentially identify regions of the genome that might be useful for, say, disease resistance. So how did we do that? Well, we used the concept of collinearity and gene synteny to begin to examine gene copy number variation in maize. And this is essentially a toy example of what that looks like. So I've got two hypothetical pangenomes, pangenome 1 and pangenome 2. And along some section of the chromosome, you can see the genes that are highlighted here. Now I've color-coded them to make this more obvious in the diagram, but you can see in these two genomes, there are tracks of genes that are collinear in nature. You've got the blue gene, the orange gene, gray gene, etc. And what we would do indeed is call these two blue genes a pair of syntalons. They share a syntenic relationship. Similar to these green genes here, they also share a syntenic relationship. Now, this is important in itself, figuring out what are the corresponding genes across different assemblies. But it also gives the opportunity to assay differences in gene content between lines. So, for example, you can see pangenome 1 lacks this peach gene here. It's just totally absent. So we could begin to identify that as a putative gene presence-absence variation. And what you can do is do that genome-wide. What I have here is a dot plot here, which demonstrates what that looks like across the genome. On the x-axis here, we've got an inbred 2, let's call it, and the 10 chromosomes are stacked up along the x-axis. Each square corresponds to a chromosome. We've done a similar thing for inbred 1, and you can see this clear axis of synteny between these two inbred varieties. And you can also note there are regions of the genome, you can see them here and here, where there are indels that are apparent, and also some large structural variations. This one here actually corresponds to the smaller of the two inversions I showed you earlier. Now, interestingly, and this goes back to my history in polyploid research, you can actually see the historical echoes of an ancient whole genome duplication that occurred in maize around 10 to 12 million years ago. If I take chromosome 1, for example, of inbred 2 and trace up the other chromosomes of inbred 1, I see that chromosomes 1 and 1 match very well. I can see this obvious collinearity and synteny between them, meaning they have the same genes in the same places in the same order, more or less. But you can see other patches of other chromosomes where there are tracks of shared collinearity, and you can see them particularly noticeable in chromosome 5, just here, and in chromosome 9. Of course, similar regions are scattered in other parts of the genome. So we can look at this broadly across the whole genome and in many different lines and begin to dissect what gene content variation looks like. And so we did that for the maize nested association mapping population, which is publicly available. There are 26 or 27 founders of that population, and Corteva was involved in the sequencing of their reference assemblies. And so we took some time to characterize the gene content among that material. And we analyzed in total nearly 1 million genes. And we observed over 13 million syntenic relationships between those genes. And we immediately asked the question, well, what are the collection of core genes in among that material? So what do I mean by core genes? I mean a gene where every single inbred that's being considered has at least one copy of that gene. So no matter what inbred we looked at, we were able to find a copy of that gene. And we could see that I was kind of surprised by this number. It's not particularly large. There are about 16,500 of those core genes that were represented in every single one of the inbreds. And what you can see is that breaks out into really two categories. One is a single copy category, where every inbred has exactly one copy. And the other category, multiple copies I've called here, is where each inbred has at least one copy. So it could be 1, 2, 3, or 4, etc. And you can see on the right-hand side here the distribution of the number of inbreds where we find each gene across that analysis and what that looks like. And you can see that there's actually quite a large number of genes that are at this end of the distribution, where we find them in only 2, 3, or 4 of the inbreds that we analyzed. And of course, this sort of begs the question about whether these annotations, gene annotations, are actually really good annotations or not. And we have in fact spent some time trying to refine our annotation set based on this sort of information. Okay, so we've taken a look at all of that variation, and I've summarized it for you. And this now I'm beginning to bring in some the phenome information, phenotype. But before I do, I just want to show you this heat plot, which describes for a particular region of the genome the copy number state of a series of genes for some of those NAM founders. So in this example, each column corresponds to a particular inbred, and each row is a gene. And the color of the corresponding cell indicates the observed copy number for that gene. And there are a couple of interesting observations you can make right off the bat. One is that gene presence absence variation is incredibly pervasive across this material. There's plenty of it. And secondly is that some genes, you can see them, they're generally highlighted with darker colors here. There are several genes where increases in copy number tend to be common across that material. So one of the things we asked, see if we could look into with this data is, are we able to make any inference about phenotype based on this sort of gene copy number information? And so what I want to do is share an analysis with you that we did regarding that. And so what we did is essentially assayed over 26,000 inbred lines for gene content variation. And then we intersected those 26,000 inbreds with those where we had phenotypic data. Here I'm showing you data for an unnamed disease. And we were able to perform a GWAS analysis to look for signals that might indicate resistance to this disease, but only using gene content variation as the input. And you can see that we get some very clear, nice signals here in this GWAS, which may, be able to help us target regions in the genome that are of interest when it comes to that particular disease. Okay, so I'm going to move on now quickly to talk about a deep genome project. So this is a project where we've brought in other omics technologies and laid that on top of some of our pangenome work in an effort to understand the biology underlining those DNA sequences, and in fact to begin to understand expression better and hopefully highlight regions of the genome that would be amenable to gene editing. And that involves bringing in ATAC-seq, which is essentially an assay for chromatin openness, the chromatin state at a particular location in the genome. We've got isoseq, which gives you full-length gene models essentially, and of course we've got RNA-seq looking at expression of those genes. And we've spent time looking at that data and how it relates to the molecular phenome, so to metabolomics based on GCMS and hyperspectral imaging. Unfortunately, I don't have clearance to talk about those specifics today, but what I do have clearance to talk about is looking at some of the ATAC-seq data. So here's a diagram here of a brief outline of how this technology works. What it does is relies on a transposase that can get into the DNA when it's not tightly wrapped around nucleosomes and tag that DNA. You can then eventually align that DNA to the genome and figure out where these regions of open chromatin lie. And this is what it typically looks like. What we have here is just some gene annotations on the x-axis and some genotypes from our elite material on the y. And what you could see is that in regions that are really distal to genes here, that are not over the genes themselves, nonetheless, we get a stacking of these ATAC reads, indicating that these are likely regions of open chromatin in and around genes. And what we can see from the distribution here is that indeed many of these peaks, these ATAC-seq peaks, do align very closely to the transcription start sites of genes. So there's some suggestion there, of course, that they're going to provide interesting regions of the genome that we could use to control gene expression. And what we've seen, of course, that we know from gene expression data is that one of the biggest drivers of differences in data sets is, of course, the tissue that which you sample. You can see here on this middle plot, the first principal component of this RNA-seq data is, of course, the tissue that was where the RNA-seq was extracted. But interestingly enough, you see similar patterns when it comes to ATAC-seq peaks. Those peaks, the first principal component is also relates to tissue from which you are sampling. So we know that we need to be tissue specific when we're hunting for regions of the genome to edit to, let's say, enhance expression of some gene that we think might impart some useful agronomic or improve some useful agronomic trait. So I'm going to move on to really the sort of
another problem, guys, but Simon, can you hear me? Not? So we will stop here and we'll restart in a moment, okay? So see you soon.
It's a little bit funny, this feeling inside. I'm not one of those who can easily hide. I don't have much money, but boy, if I did, I'd buy a big house where we both could live. If I was a sculptor, but then again, no, or a man who makes potions in a traveling shoe, I know it's not much, but it's the best I can do. My gift is my song, yeah, and this one's for you. And you can tell everybody this is your song. It may be quite simple, but now that it's done, I hope you don't mind, I hope you don't mind that I put down in words how wonderful life is while you're in the
Hi again. So, guys, we will stop to the break now. We had some problem in our transmission here, but take this moment to drink a coffee and water, and we'll see you in 15 minutes. Okay? See you.
I sat on the roof and kicked off the moss. Well, a few of the verses, well, they've got me quite cross. But the sun's been quite kind while I wrote this song. It's for people like you that keep it turned on. So excuse me for getting, but these things I do, you see, I've forgotten if they're green or they're blue. Anyway, the thing is, what I really mean, yours are the sweetest eyes I've ever seen. Tell everybody this is your song. It may be quite simple, but now that it's done, I hope you don't mind, I hope you don't mind that I put down in words how wonderful life is while you're in the world. I hope you don't mind, I hope you don't mind that I put down in words how wonderful life is while you're in the world. It's a little bit funny, this feeling inside. I'm not one of those who can easily hide. I don't have much money, but boy, if I did, I'd buy a big house where we both could live. If I was a sculptor, but then again, no, or a man who makes potions in a traveling shoe. I know it's not much, but it's the best I can do. My gift is my song, yeah, and this one's for you. And you can tell everybody this is your song. It may be quite simple, but now that it's done, I hope you don't mind, I hope you don't mind that I put down in words how wonderful life is while you're in the world. I sat on the roof and kicked off the moss. Well, a few of the verses, well, they've got me quite cross, but the sun's been quite kind while I wrote this song. It's for people like you that keep it turned on. So excuse me for getting, but these things I do, you see, I've forgotten if they're green or they're blue. Anyway, the thing is, what I really mean, yours are the sweetest eyes I've ever seen. And you can tell everybody this is your song. It may be quite simple, but now that it's done, I hope you don't mind, I hope you don't mind that I put down in words how wonderful life is while you're in the world. I hope you don't mind, I hope you don't mind that I put down in words how wonderful life is while you're in the world. It's a little bit funny, this feeling inside. I'm not one of those who can easily hide. Isn't she lovely? Isn't she wonderful? Isn't she precious? Less than 1 minute. Oh, I never thought true love would be
Hi again. We reconnected with Dr. Simon, and he will present your lecture. Okay? So, Dr.
Yes,
Simon, can you continue?
I can. And my apologies for this interruption. I'm not sure what happened, but technology failed me at some point and I was disconnected. So my apologies.
Yes, it's happened.
All right, so let's start quickly so that we can catch up some time talking about the last piece of my talk, which is really covers some of the machine learning and environment piece that we've brought together that helps us position products, the right products in the right acre, and maximize the utility of our products to farmers. So as you're probably well aware, in a company like Corteva, there's typically a lot of data. We've been collecting data for years, as we have hundreds and thousands and millions of inbred lines of maize that we've used over the years, and we have plenty of R&D sites where it's assessed the value of that material. But the very nature of that data is that it's it's sparse generally, and we don't have all genotypes in all environments. In some environments, we have many genotypes, and some locations we have only a few, and so on. And so, machine learning turns out to be an excellent way to address some of those issues that present problems with other types of analyses. And so this concept of a right product, right acre really sort of comes down to this sort of a G by E problem. And here's a few diagrams that really describe that problem. On the left-hand side here, we've got the no G by E situation. You've got two different genotypes, A and B, in two different environments, A and B. And the relative difference in their value is the same regardless of the environment. And so there's really no interaction there. And then you've got variance G by E, where you can see in the middle plot here that genotype A, the relative value of that genotype increases relative to genotype B in this new environment. And then you've got this rank shift crossover, which happens. And this is the sort of thing I'm going to focus on going forward, where the actual relative value of these two genotypes switches depending on the environment. So we took an analytical approach to this and used environmental data. You can see what the feature set looks like on the left-hand side of the slide here. I won't go through all of these different features, but they're used in conjunction with the genetics piece, and our trait of interest, let's just say yield, is a function of how that feature set interacts with the genetics. So, traditionally we would use a supervised learning approach like a linear regression or something along that lines. But as I mentioned before, the sparsity and the limited labeling of the data often limit our ability to take advantage of the information we have. And as I mentioned before, sometimes these models tend to have weak generalization. They don't necessarily predict well on new genotypes or new environments. And you can only really learn the direct relationship between your features of interest and your targets. So what we've done is taken a self-supervised learning approach using partial features of X, which is what you in the end want to use to predict on, and use a neural net-based approach to learn something about the structure of that data and how those features of X interact with one another. And of course, what we can do is generate latent representations of them. So we've done that for environmental data, but we've also done it for genotype data. And a classic example of this self-supervised learning is genetic imputation. You can use partial genetic information, genotype information, and a setup like this to learn how to impute a more complete genotype representation via this structured latent representation. So we've been through this process for the environment data and the genetics data. And then what we can do is bring that information together into a single piece and use that to predict some target Y. In this case, what I'm going to tell you about the target here is not yield in itself or any other harvest trait in itself, but it is a prediction on, given two hybrids, which of those is likely to outperform the other in a given environment. Before I get into the details of that, I just wanted to show you this UMAP embedding of some of the environmental latent space encoding that we developed with our neural nets. And you can see it's quite structured and it breaks out by year. And there are some interesting parts of this plot, like these guys over here, which are actually from drought regions and do differentiate from the rest and typically don't cluster by year. All right, so this is what we can do with these models that we have set up. We can interrogate a collection of hybrids to find out or to predict which might be best in a given environment, given all of those features that I showed you in a few slides previously. And so what we have here in the top level here, we have a non-irrigated environment from 2012, which we've classified as high stress. And what you can see is on the x-axis, we have relative predicted performance, and each of these bars is the performance of a given hybrid. What you can see is that a high yielding product, which we would usually suggest to farmers when conditions are ideal for growing, that usually yields very highly, is actually not predicted to perform very well at all. You can see on the right-hand side of this plot here. Whereas a well-known drought-resistant hybrid is predicted to perform very well. If we then stick in the same area of the country, but this time say that location is now irrigated, so it's a moderate stress location now, what we see is the relative predicted performance of those hybrids completely switches. And so we can use this sort of information in conjunction with what we know about a particular field to suggest which hybrids might be beneficial to plant. Here is an additional slide that shows how these models work. And what I'm doing here is sharing with you some SHAP analysis. And I won't go into the details of exactly how that works, but what this does essentially is, given the features that you impart to your neural network, it tries to figure out which of these features are actually having a greater impact on the outcome of the prediction. And what we see is when we look at hybrids that are late versus mid-maturity, we find that the feature that the SHAP analysis picks up on is flowering high temperature. That's the one on the top here, like that. And you can see how the environment locations break out on a map of the United States here. This is from 2018. You can see that mid-maturity products are predicted to win right across that mid-maturity maize band. On the right-hand side here, we've got a drought-resistant hybrid versus a top-end yielding hybrid, similar to what I showed you in the previous slide. And the SHAP analysis suggests that irrigation is, in fact, a really crucial piece to predicting this outcome. And what you can see is that really the drought-resistant line winning, which is indicated in blue here, really is in only a minority of the locations. And across the traditional corn belt of maize, you see that it's actually the top ending yield product that is generally predicted to win out. All right, so in the interest of time, I'll just try and briefly get through the summary. I've just covered what we do as with pangenomics at Corteva, and how having a pangenome set that's tailored to exactly your needs is crucial. I've also shared with you how we've looked at other omics technologies, particularly ATAC-seq, to begin to highlight regions of the genome that might be useful from a gene editing point of view. And then there's bringing in gene content variation and combining that with phenotypic analysis to look at various traits of interest and use that gene content variation to predict putative regions of the genome that might be of interest. And I've just closed out with a description of how we're using deep learning technology coupled with Envirome and Phenome to begin to drill down about product placement and help farmers to place the right products in the right environments. So I just want to put this acknowledgement slides up very briefly here and acknowledge all of these co-workers who have helped generate some of these slides and put together all of this analysis. I thank them all. And we don't have time for questions, but if you do have any, you can reach out to me at this email address and I will endeavor to answer them as best I can. And I just want to say thank you for the opportunity to present, and I apologize for the interruptions, and thank you very much.
So it was excellent lecture, Dr. Simon. Thank you for accepting our invitation and share your knowledge and experiences with us. Okay. So
thank you.
Unfortunately, you can't participate in our roundtable, but we thank you a lot. And,
yes, thank you all for listening and inviting me. I appreciate the invite.
Okay, thank you.
Take care. Goodbye.
Goodbye. So, continuing our event, I would like to invite Dr. Seth C. Murray, professor in agriculture and life science at Texas University, to present the third lecture of the day. Hello, Dr. Seth. How are you?
I'm excellent. I need to remember to unmute.
Okay, no problem.
Thanks for having me.
So thank you very much for accepting our invitation. It's a pleasure to have you here. So I will present you. Dr. Seth Murray received his PhD from Cornell University and your bachelor from Michigan State University. His research program focused on approaches in high throughput field phenotype, including unmanned aerial vehicles like drones, quantitative genetic discovery, gene to fin data and analytics, and applied maize breeding in Texas, as well as perenniality in maize and sorghum. He has released 90 maize lines, some having been licensed and being grown by Texas farmers, including proprietary hybrids for whiskey. In 2016 to 2017, he served as the senior advisor of agricultural system in the office of the chief scientist at the USDA. He founded and served as editor of the Plant Genome Journal and ASA and CSSA publication. So, thank you again, Dr. Seth. The audience is yours.
Thank you, John and Rosamara. Great to be here. Really happy to have the invitation and the pleasure to talk to you. I've had a few Brazilian students over the years and many Brazilian colleagues, and I'm very honored and blessed to be fortunate to present to you and work with you guys. So I switched up my presentation a little bit from what I normally talk about based on some conversations I've had with people and some confusions about phenomic approaches. So hopefully this is clear, and if not, I encourage you to email me or ask questions. So what we really want to talk about today is nature and nurture. I think what you've heard about a lot is nature or genomics. And so nurture would be capturing a lot of the phenomic aspects of plants. So I am an applied maize breeder. And so I think it's always important to say that, because every tool that I use and develop has to fit in the context of an applied breeding program where we are always short in labor. We're always trying to do too much and have too many projects going on. And so that's a big context of where I'm going with this. If you look at corn in the United States, of course, the vast majority is in the Midwest. And we just heard from a Corteva personnel. And that's where a lot of industry is focused on breeding. Let me do the pointer here. A lot of industry is focused on breeding. Unfortunately, in the South, which is a growing maize growing region, we don't really have any industry breeding per se. There are a couple locations in Mississippi, But for the most part, the varieties that are sold in the southern United States are bred and developed in the Midwest and then sent down here. And you can imagine that's quite a bit different. So that's part of the reason that we actually have a public corn breeding program. I'm one of the last public corn breeders in the United States. For the most part, other people are doing corn genetic research, but not actually trying to develop varieties that would be commercialized. And so the black line here just shows the US average yield of maize. The red line shows Texas, and this bump right here is because of the irrigation in the high plains of Texas, which is a high yield environment. And then my target environment is actually this sort of grayish brown line. And that's lowland, mostly non-irrigated acres. And the yields are pretty low, much lower than the US average. And so we have developed a lot of unique germplasm, some that's being grown commercially. Most of our germplasm derives from lowland Bolivian and Brazilian germplasm, most of our successful material, with a lot of cimet and other stuff mixed in. And then we've also got a lot of temperate Midwest that's been crossed to that and been recycled. And aflatoxin and corn breeding for whiskey have been some major focuses over the year in traits. But really, we're interested in breeding for more than just yield. I know that's really the thing we always talk about is yield, yield, yield. But really, at this point, we're talking about farmer profitability. We're talking about human health and nutrition, reduced input use. Ecosystem service provision is increasingly a large one. And now climate change resilience. This year, we had another record heat wave here in Texas. I think it was 60 days over 38 Celsius or something like that during the growing season, which was very stressful on the plants. So he mentioned briefly perennial corn. I do just like to point out that perennial corn is a good mechanism of stress resilience, potentially, because it's evolved to capture growth during the coolest and wettest parts of the year in the spring and the fall, whereas our commercial corn that we currently plant mainly has to fill its grain during the hottest, most stressful and driest period. So we can see in some of the wild species, we still have root growth after the normal Zea mays hybrids have senesced and died. And hybrids are somewhat intermediate to that. But this is a long-term project, probably not a lot of interest to most people in this group. But the tools we're developing are able to be applied to these types of questions as well. So I'm hoping Diego showed you guys all this this breeder's equation. I'm hoping you're very well familiar with it. But it's important to keep in mind that this is really what we're focused on. We want to make genetic gain over time. And we do so by growing more plants, increasing selection intensity, and selecting plants better, selection accuracy, measuring the plants better. And I'll talk to you about that a lot today. Additive genetic variants, so being able to use more genetic diversity and screen more plots too. And then years per breeding cycle. So to give you an indication in my breeding program, and this is from our winter nursery, we grow about 17,000 yield trial plots and about 10,000 nursery plots each year. Of course, the private sector is much greater than that. They're focused on developing mega varieties to cover the United States, whereas we're sort of targeted this southern United States stressful environment. And I also need to mention, unfortunately I missed Diego's presentation, the Genomes to Fields project, because we need to be able to use this genetic diversity and leverage what people are doing in other locations. So the Genomes to Fields project will come up a little bit in this. In our environment, what we actually do for Genomes to Fields is we grow three environments or three management conditions. We grow an optimal management, we grow a dry land management, so optimal would have irrigation, and then we grow a late planted irrigated. And the late planted irrigated is probably the most relevant towards stress tolerance because the plant experiences higher temperatures early on, and that stress is really unique to see on some of these plants. So the last couple talks really focused on the molecular genetics side. And I just want to remind everybody that, molecular quantitative genomics and statistics really has helped increase the genetic gain equation. So this is just an example from our magic population. It was a 4-parent maize population where we compared different mating types. But we also only were able to find a few loci. Unlike what's normally expected with QTL mapping, the larger the population, the better your detection ability. We were rather disappointed in the results. And that's part of the impetus for me to start looking for other tools in my breeding program. So there's been three major genomic methodological waves. So in 1986, and I'm assuming many people are familiar with this, QTL linkage mapping came on the scene. And the goal there, of course, is to find loci, to do map-based cloning and find genes, usually using biparental families. But the inference that's been able to be made, the loci that have been detected there, don't necessarily translate to other populations or other environments. So it's generated a lot of knowledge in publications, but I struggle to point to too much crop improvement that QTL linkage mapping has developed. In 2005, we started to see association mapping, especially in maize. Same goals, but using diverse populations and alleles across population structures, especially when you're doing GWAS in hybrids, as we've done. It can be quite powerful to find important loci. But again, for my program, it generated knowledge, publications, but no crop improvement. And so in 2007, we started to see with Bernardo and you and other many, Mioisen and many other folks, genomic selection coming on the scene. And it's important to remember the goal of genomic selection is very different. It's to select the best individual, not to look at loci. We've seen populations varied in this. We've seen the type of training that's been done quite a bit varied. And it's generated a lot of crop improvement and a lot of knowledge, but it hasn't generated so many publications because the predictions developed for genomic selection are not necessarily translatable to other environments. Right. And so I'm only framing that in the standpoint of how we're going to talk about phenomics, because people struggle with this concept of phenomics. And so I'm hoping that thinking about it in the context of what's gone on in genomics will help you think about what can go on in phenomics. So the original genome of maize by Emerson was mostly used with morphological markers, and it was very sparse. Right. And then in 2005, with the IBM population, it was saturated, and we can see how many markers are on the primary chromosome 1. Not very many. In 2013, Romay et al. Published 681 SNP markers. And then I just found in August of this year, a large group published 12.2 million SNPs on 1,500 inbred lines. So I think it's fair to say we've saturated the genome, where we have enough markers that we can pretty much predict what every other locus would be, through various methods. And that a lot of that comes through the decreased cost in DNA sequencing, as we know. But I don't hear anybody talking about saturating the phenome yet. Okay, and so that's the context in which we're going to really begin getting into phenomics here. So this is a silly example of my family, but you can think about your own family, and you probably have relatives. So I have one sister, and you can see from this picture that my sister and I look somewhat similar, and we both look like our parents. But if you asked somebody why we look similar, they might point to the hair color, or maybe the eye color, maybe the lip size. But we as humans would struggle with figuring out features that are, really identifying how individuals look alike. But we can see that resemblance. We've evolved to see that resemblance. Furthermore, in the context of what I'm going to talk about later, my sister and I look similar later in life. Okay, so we still have facial features that look similar, but we're different here than we were earlier in life. So our facial features are the combination of nature, right, genetics, plus the environment, G by E, and then, management. So we know people, for instance, who grow up in war zones or malnourished. The two siblings will look similar, but they might be a foot shorter than if they were, well-fed. Okay, so that's a context I hope everybody can think about. We also know that individuals that are related in this way perform similarly. Have similar intelligence levels, maybe similar athletic abilities. So there's a lot of correlation there. And my posture here is that this phenomics approach of capturing these appearances, which would incorporate environment, G by E, and management better, is more predictive of performance than genetics alone. Recently, I was talking to a prospective graduate student, Masambola, who made me aware of his work and some other work looking at facial features in goats, is what he did. But there's a group that's shown heritability in facial features through a GWAS analysis in the Han Chinese. There's another group that's looked at deep face models and where various features are corresponding to gender or age, right? So wrinkles tend to show up around the mouth, for instance. So we know that we have facial features that could be used in somehow looking at relatedness or phenotyping, okay? So this is going to really correspond to the end of my talk, but I want people to be able to think about, how we would measure more features in humans or plants. So let's jump into high throughput field phenotyping. So what most people so far, unfortunately, think of high throughput field phenotyping as is a way to automate routine measurements. So, we measure plant height with a yardstick. Can we measure it with a drone or a vehicle, right? Or we can measure grain yield in sorghum and wheat where the panicle is up. You can actually count the grain and estimate grain yield. Or disease, and I'll show you examples of the things in green here. But what I'm really interested in is finding new signatures of leetness. So temporal growth patterns, like I showed you, how my sister and I look similar, but at 2 different points, that's a richer feature of data set, right? It's how we interacted with our environment over the years. Senescence and grain filling period I'm going to talk about. And ultimately, that'll lead me to phenomic selection, which I think is probably going to be the most game-changing technology in plant breeding, in decades. Now, what's really interesting here is all these things that we discover as being useful can also help farmers in stress signature management. And I'll show you that example in the estimating disease. It'll also help us identify new phenotypes and mechanisms of biological importance that could be used in something like gene editing, if you're interested in that. And I'll show you an example of that as well. I'm not going to spend time talking about the process of going from UAS or drone or whatever you want to call it data to making useful decisions. But this has taken a number of collaborators and my group. We've been working on this for 7 years now, so that it's much more routine. And the people here deserve a lot of credit. There's a couple others I'm not showing, and Reagan made this slide, just showing the whole pipeline and workflow of flying the UAV, which is actually probably the easiest part, and downloading the images, to the orthomosaicing process, developing shape files, the FACT4 process, masking soil, extracting vegetation indices. And of this whole workflow, the only thing I personally, as Seth Murray, know how to do is about here in the analyzing data part. The rest of this has all been my awesome students and colleagues. Oops, looks like, there we go. But there's still problems with these tools. So this is an example from Aaron. You still get hot spots, this bright spot here, or distortions. And, collecting the data is still not a perfect process. It's akin to trace files when we were doing SSR genotyping back in the early 2000s. For anyone who is using UAS tools, I do like to point out that Stephen Anderson and I wrote a R package to make these shape files. When you start to deal with thousands of plots in your breeding program, and you need to extract information from each plot individually, you really need a tool that can help you draw those plot boundaries. And so in this, all you need is your breeder's field book and 2 field coordinates, and you can get the shape file to extract features from everything. So I'm going to go way back to our very first publications in this area, plant height, just because I think it's nice to show how plants grow over time. So on the y-axis here is the days after planting. Actually, these are calendar days, I believe. Calendar days in the year. And this is showing 2 different drones, a tough wing UAV mapper and a copter. And this is just plant height in those 3 genomes to fields trials I mentioned, the late planting, the optimal planting, and the dry land planting. And these different lines are different genotypes. So what's unique about some of these lines is there are a few crossover effects, meaning the information that you find early in the season is not necessarily predictive of what you'll find later in the season. And so that means we have additional SNPs or features we could use in our phenomic prediction models. I'll point out that, that in this case, we actually had better correlation to grain yield with the drone data than we did with the manual data. So this idea of using the manual data with a yardstick as a reference for measuring our plants is probably pretty antiquated. The drones are probably going to do a better job. I want to have some connection to genomics here, so I'll just show you this one study that was published a few years ago by Stephen. And what he did was use those plant height models to estimate the plant height in QTL linkage mapping populations on every day of growth. And what was interesting is we map QTL and we see that some QTL actually happen early in the season and then basically would be non-detectable by the later part of the season. So if we're really trying to get to the biology of the plant or where we can make the most progress, we tend to measure plant height at the end of the season, and we're missing out on all this important information that's segregating and we can select on earlier on in growth. So let me tie these two things together and start talking about vegetation indices. So Natalia Cruzado is a Brazilian. She was a PhD student with me. She's currently working for Corteva. But she was looking at NGRDI after in a population, I believe this is genomes to fields. And there are 3 commercial hybrids here that are completely unrelated to our knowledge. They're from 3 different companies, so we expect they're unrelated. And then we have 4 half-SIB hybrids, all with a common parent of TX714. And what we can see is the overall vegetation index is more similar for these half-SIBs than it is for these unrelated commercial checks. So if we think about what that means, that's much like what I was showing with human faces, where relatives that are more similar are going to show features that are more similar, and it's our job to start measuring them and developing a rich data set. So I'll jump to rust and senescence, and this is a little bit more of a story, and this is part of Aaron DeSalvo's PhD project, and this has been published in scientific reports. So we were looking at southern rust and senescence using high-throughput field phenotyping. So southern rust is a problem here in Texas, and we could go out in the field. I, as a breeder, have gone out to the field to rate hybrids, but it's really laborious, and it changes from day to day. So I don't know if I got the best day when I go out and screen that population. And furthermore, it's sort of somewhat subjective. I'm kind of guessing. And so what Aaron did was he actually developed this rating scale and rated UAS or drone imagery. And the idea there is that, first of all, we can develop an algorithm to predict this. And second of all, that's the training data set that can be used for AI approaches later or machine learning approaches later. The benefit here from a farmer perspective is, well, maybe we can catch this earlier and be able to apply a fungicide treatment. So this is just a little bit of a cartoon here showing 2 years, 2020 and 2021, and the various dates that the drone was flown. My program tries to optimize collecting the most drone data throughout the year. We don't target any specific trait. And that's what's really allowed us to develop phenomic selection methodology and other calibrations that were never pre-planned in the experiment. So we know the plants grow, they flower, they set seed, and they senesce, right? And then something like southern rust hastens their senescence. And we can see from false color images using some vegetation indices that it's very clear that like this plot has senesced here, whereas this one is still nice and green. Okay, so we can see that with our eye. How do we get the computer to actually do that, to actually identify that? Now we could use an AI approach, but it may not be interpretable. It may not be able to be ported over to other populations or other environments. And so we mainly just focused on the vegetation indices here. So I think I already told you this, 13 flights, 17 flights, senescence scores. Dr. Scott Wild was one of the people who flew, and Aaron flew in 2022 along with Reagan. Okay, so here's an example of some of the vegetation indices. And I think now for multispectral, we extract about 86 vegetation indices. For regular RGB cameras, we're extracting about 20, 30, somewhere in that neighborhood. And so each one of these is a different vegetation index. So that's the blue channel by itself. And then here's excess green, for instance, which is fairly predictive. BCC is a really predictive one that we see. NGRDI is a common one. And we can see these different patterns. And across the 2 years, the patterns don't necessarily line up. So in a phenomic prediction model, and this isn't the true phenomic prediction, this is sort of just simple cross-validation. I probably should change the title here. We're using a training data set and then a test data set to look at predicting senescence from these vegetation index scores and predicting rust from these vegetation index scores. And so what we see, first of all, is that these vegetation indices are heritable. So the temporal repeatability, or essentially heritability, is bouncing right around here between 25 and 50% for each one of these vegetation indices on the y-axis. We break this down into a model of flight, because obviously when you're flying at seedling, it's very different than when you're flying at flowering, and very different when you're flying at senescence. Pedigree explains only a small amount of information, but that's only because flight so overwhelms the amount of pedigree information here. We fit some spatial models as well, range and row or row column variation, rep, and then we have a residual. So the first thing to really note about these vegetation indices is that they are highly correlated between each other, but within a growth stage. So in this example, we've laid out all of the vegetation indices together by date. So this is flying in seedling at this end, and this is flying mature plants at this end. What we can see here is probably the vegetative to adult plant transition. And then the other thing to note is that it's very different between years too. We see these vegetation indice correlations quite different between years. I do need to point out, because we've had a lot of criticism of our phenomic methods, that there's a lot of multicollinearity. And so Alper, and he asked me to put baby doctor, he's our newest PhD in the program. So he's going by baby doctor these days. If we look at these various dates, and here's multispectral phenomic data from 2018 dry land, from 2018 irrigated, from 2017, from 2018 dry land, from 2018 irrigated, and then here's genomic data. What we can see is that the genomic data actually probably has higher multicollinearity than our vegetation index temporal approach. And so for people who are critical of this, this is one thing we can present, and the other is that we use machine learning methods so that multicollinearity is reduced as a problem. To go back to rust, the heritability of southern rust was very high. Again, mostly genetic with range row variation, rep, and some residual. Senescence, we actually looked at on a temporal scale, and time is again the biggest variance component of that, with a lot of genetic variation. But the repeatability of senescence was 0.6 to 0.9. Variable importance scores is another way to look at this. And so in this case, RCC, which is a vegetation index, for senescence at 112 days in 2020 predicted the best in early growth. So what this suggests, although it could be an artifact, and that's what subsequent validation studies are needed for, that we can predict the senescence of some of the plants. This is not perfect correlation, but this is a high correlation. We can predict the time a plant will senesce based on early season growth. So that's part of the power of phenomics, is if we measure enough things, we eventually will saturate the phenome and we'll be able to predict things that we never intended to previously. The really exciting part for me, and what's really catalyzed Alper and Aaron's future work, was this figure here. So on the bottom of this figure is yield. And what we can see is plant height, which we know is highly correlated to yield, is correlated to yield. But we were really surprised to see that senescence was correlated to yield. And then the difference between senescence and flowering time, which we call grain filling, was very highly correlated to yield. So this phenomic measure of senescence that Aaron did by visual observation and then developed the calibration using vegetation indices is predictive of yield in our segregating populations. So using various machine learning approaches, they've now been able to figure out, rust, for instance, has an accuracy of about 0.75, and that's in CV1, and in CV2, it's a little bit lower. So the linear model in this case, once we get into something like CV2, CV3, CV4, performs quite poorly. And that's probably largely because of that multicollinearity problem. Now, Alper's taken that a little bit further and started modeling senescence using those scores. And so this is an example for anybody who may not be following me here, with two genotypes, genotype A and genotype B, the date that the plant silk to the date that his remote sensing, his UAV senescence measure is taken, is what we call the grain filling period. And so we can have two genotypes with dramatically different grain filling periods. And so when we talk about plant stress, the grain filling period is one of the biggest indicators of what can survive through plant stress. Because if you flower and then you're able to fill the grain for a very long time, your yield is typically going to be much higher than if you flower and as soon as drought comes in, you senesce. So the grain filling period and modeling that is quite important. He's found, excitingly, that the grain filling period is very predictive of yield, especially between environments. And so this is something that you don't necessarily have captured with a genomic model. So in this case, you see the late planted plants, which are much taller, and so you would think would yield higher, but their grain filling period is much shorter than something that was planted in an optimal environment. And that's really what's helping us figure out that this grain filling period can be measured by remote sensing and is predictive of grain yield. And then just one last comment on this. Alper has really continued to expand the modeling aspect of this. Now he has pedigree, flight management, pedigree by management, pedigree by flight, flight by management, pedigree by flight by management, and then row column and rep. And so these more complicated models are really going to help us get at the main effects that are genetic and are environmental and are management. I told you before about being able to predict rust and senescence early in plant growth. This is a paper that he published when he was a PhD student in remote sensing. And this just knocked my socks off. This is when I think I was completely sold on UAS drone measurements. So we have here on the x-axis, on the y-axis, various vegetation indices. And then on the x-axis here, we have the day after planting. And what actually blew me away was that the highest prediction for yield came early on in the season. So it came before the plants actually flowered. And our hypothesis on this is that everything after flowering has already been selected for by breeders for a very long time because it's been measured. Most breeders listen to physiologists who say the important part of grain of yield is flowering to grain fill, and it's that grain filling period. But oftentimes we don't even go to the field to look at the plants early on. And so by flying drones at this point, we can actually identify segregating variation we can select for that will increase end terminal yield. And that was really exciting. I think the last major component here I'm going to talk about is phenomic selection. And so to understand phenomic selection, you need to understand a little bit about near-infrared spectroscopy for those people who may not be familiar. So near-infrared spectroscopy, our Thermo Fisher Antares is measuring something like 3,000 wavelengths being reflected from corn kernels. We then take and grind those and we send them for chemical analysis. And we take that spectra and we use a partial least squares calibration to make something predictive for starch, oil, protein, etc. So this has been done for 30 years, where you would use near-infrared light to augment your wet chemistry data or your actual measurements and develop predictive equations. So we've applied that to our breeding and genetics research, and we found that the calibrations for crude protein look great compared to phosphorus, but that the genetic variation actually is about similar between these two. So that led us to an idea that, well, maybe it's not just the accuracy of the measurement, maybe it's also the number of measurements you're taking. And we found that that's true. This is a recently published study by my former student, Holly Lane, where she showed high throughput phenotyping can actually produce better decisions than high accuracy phenotyping in plant populations. So just a little aside there. So phenomic selection was initially published by Rinson et al. In 2018, and it was probably the best paper I've read in my career, or most exciting. In this paper, they used near-infrared spectroscopy that I just showed you, but instead of trying to predict composition based on certain absorbance wavelengths, they actually used it like genomic selection. What they found was the phenomic selection models in both wheat and popular was as accurate as genomic selection, but it was cheaper. And so we had a similar data set from dryland and irrigated trials. We had about 4,000 samples we'd skinned into NIR. And then Holly Lane, along with Jose Crosa and his team, looked at this data and saw, can we use this in phenomic prediction and phenomic selection? And again, the results were extremely promising. We found a high correlation for yield. And part of that was due to the protein, starch, and oil correlations with yield. One of the things I found really exciting about this that you don't necessarily see with genomic selection was that the calibrations we developed in one population and in one environment actually were predictive in another environment and in totally unrelated populations. Okay, so that led to a question: are predictions based on composition, like the protein, or are they based on relatedness, like genomic selection is? And I'm pretty confident now the answer is both, and that's why phenomic selection can outperform genomic selection. Okay, there we go. So I think this is one of my last slides here, and this is the crux of where my program is going and where I think the best opportunities are for breeding for stress environments is in phenomic prediction or phenomic selection. Alper submitted this to G3. It's conditionally accepted a little while ago, but you can access it from bioRxiv if you're interested. In this case, he did all the CV measurements using genomic prediction, multispectral prediction, and RGB prediction. And what he found was for CV2, which is one of the more important ones, right? Predicting untested genotypes in tested environments. So how would untested genotypes perform in a new or in an environment that we've measured? It did outperform genomic prediction. When it came to CV3, tested genotypes in untested environments, maybe not so much, but untested genotypes in untested environments, we see that phenomic prediction is about equivalent to genomic prediction. Okay. And in this case, he had 1,068 phenomic features, 89 vegetation indices by 12 time points, 525 phenomic features for the RGB, 35 vegetation indices by 15 time points. And for genomic prediction, he was using about 153,000 markers. So he's expanded on this into other populations now. I don't have those results to show you today, but phenomic prediction continues to look very promising. So I think I'll leave you with this. What do I believe the future in plant breeding looks like, especially for stress environments, is we're measuring certain dependent traits of interest: yield, nutrition, ecosystem service provision, whatever you'd like. We have some certain physiological measures we take and we think is important, like flowering or plant height. We have temporal phenomic measures that we measure from drone. So plant height at 30 days, plant height at 60 days, plant height at 90 days. We're going to have some segregating remote sensing measures, and that's most of what I showed you. And then we may still retain some genomic measures, but we're finding oftentimes they're redundant to our phenomic information. From all this, we can incorporate weather models, develop relationship matrices, and develop statistical analysis that are predictive of untested hybrids for untested environments. So with that, I'll end. Hopefully I didn't speak too quickly, and I don't normally present in this order, so hopefully it was somewhat coherent for you. I look forward to any questions and any discussion that may come for this, and thanks for your time.
Okay, Dr. Seth, thank you. It was an excellent lecture. And thank you again to you accepting our invitation and share with us your knowledge and experiences. So, do you have time to participate in a roundtable?
Yeah.
Okay.
Be my pleasure.
Okay, so I would like to invite Dr. Diego Yaquin to participate with us in the roundtable. Unfortunately, Dr. Simon doesn't participate in this time, in this section. Okay, Dr. Diego, where are you? I think he's not here. But okay.
Maybe I ended too early for him. He probably was going to get coffee.
Yes. Okay, I will start with a question to you. Okay?
Sure.
Okay, so what the question? Director, can you put in the screen, please? Just a moment. Okay, where? Okay, I see. Okay, so this question is from Charleston Lima. Dr. Seth Murray, how can we increase the accuracy of high throughput plant phenotyping with drones?
Yeah, thank you, Charles. Oh,
sorry.
You want me to go back to the first one? Thank you, Charles. It's a great question. Many different answers here. First of all, I would say that accuracy is overrated. I have this discussion a lot with our engineering colleagues. If I, as a plant breeder, can do something less accurate and do it, be able to expand the number of individuals I can screen, we can make more genetic gain, right? So, for so long for genotyping, we've been looking at how can we maximize the number of genetic markers. Whereas for phenotyping, people are so concerned about accurately measuring traits that have been measured for 60 years, rather than saying, okay, how can we maximize the information content from that phenotyping, right? The other thing I would say is it depends on the trait. So if your goal is to measure stand count, that's a mature technology and operationalized by a number of companies already. They already can tell you the stand count. Plant height is pretty much a solved problem, pretty easy to do in most crops. As we start thinking about things like senescence or rust or grain filling period, I think it's just going to take time and people working through it and developing new methods. And so we need as many bright people from different disciplines working together on these problems as possible. So hopefully that helps.
Okay, so we have another question from Charleston. Can the LiDAR sensor light detection ranging and digital surface model be better than vegetation index?
So I would say, again, it depends on the trait. LiDARs are only going to be useful for structural information. So plant height, leaf angle, maybe flowering when the tassel or panicle comes up. They are fairly information poor and data rich. So again, I'm trying to maximize the amount of phenotypic data I can get with the minimal amount of effort and cost. And an RGB camera on a drone, we primarily have been using a DJI Phantom 4 or a Phantom 4 Pro RTK multi-spec, $2,000 to $10,000. As soon as you talk about a LiDAR, you're talking about a $60,000, $80,000 UAV package. And if you crash it, you can't use it. If you want to extend that to your collaborators who only have a few $1,000s, you can't. So RGB cameras are, I think, still underrated for the power in plant breeding that they have to offer. Hopefully that helps.
Okay, thank you, Dr. Seth. We have another question here. It is from Rosemara Barbosa. Excellent lecture, Dr. Seth. How you can correctly separate biotic and abiotic stresses in the field using digital images? Some diseases have the symptoms similar to abiotic stress.
Yeah, so two answers again. The first is depends on the trait, right? If you're actually, if you have lesions like northern corn leaf blight, Mike Gore's group at Cornell did a great job using artificial intelligence to phenotype northern cornleaf blight with characteristic lesions. But again, the thing that's different that people really are struggling with is they're focused on traits and traits they're familiar with. And if you're focused on trying to measure a trait that you're familiar with, you may be missing easier opportunities to measure something that's more predictive or more exciting. And so by measuring in the field, for instance, leaf rust, so Aaron goes out and measures, rates leaf rust. And then we have a rich data set of phenomic vegetation indices throughout growth temporally, and we can develop predictive models. That's a much easier way of approaching the problem than saying I have this certain type of lesion or I have this certain type of coloring. How do I separate these two? You could spend a lot of time on that. Whereas really, if you can phenotype, whatever the end trait is that you're interested in, just apply the phenomic measures to that. I'm not sure if that helps, but it is a different way about thinking. It's a very different way of thinking about phenotyping than the way that is normally presented.
Okay, I had a question for you. So, you said that you know some Brazilian guys and work with some of them. So, I'd like to know if you have some program to receive Brazilian or people from other countries in your laboratory.
Yeah, I'm always happy. I mean, the most productive and most enthusiastic is Dr. Gustavo Hugo, who's now a professor, also a master judo expert. But he brought his popcorn samples here. We grew his popcorn here, and he did near-infrared spectroscopy. Natalia Cruzato took advantage of a PhD fellowship that Monsanto, before they became Bayer, offered at Texas A&M to 3 students. And Jalis Fonseca was also here under that program. And now I think he just went to go work in Bayer. So sandwich programs and fellowships have been the primary way. Some students come in on a grant, but yeah. I invite anybody interested in this, we'd be happy to try and figure out how we could host them.
Okay, I will send an email to you.
Okay.
Okay, so we have more questions from our audience.
Did we lose Dr. Diego?
Yes, unfortunately.
Oh.
So if you don't have more question, thank you so much, Dr. Oh, Dr. Diego, come back.
Yes, I'm sorry. Sorry.
Oh, Dr. Diego. Okay, good to see you. We have some questions for you here, okay?
Yes, I'm sorry. As I said before, I'm traveling here in Colombia and Seattle, and I was in meetings the whole time, but now I have time. Thank you.
Okay, no problem, man. Okay, so this question is from Rosemara Barbosa. Between the multiomics that you see in your work, which have been presented the best results for the understanding of phenotypic responses and the selection of superior genotypes? I think
yes.
It's continue. Okay, these tools are expensive. Could be applied in a breeding program at the Brazilian university with few money.
Okay, thank you, Rosmaria, for the question. Actually, yes, there is one of these layers. I mean, if we say multiomics, no use restricting to the case of the genomics, I would say that the most interesting and most powerful way to conduct predictions is the way that for sure was introduced by Dr. Murray, so using phenomics. That's the most powerful way to do it. Now, there are some things or issues that we still should consider to fully apply these methodologies, because not some cases, but in general, we need to plan these genotypes in fields in order to take the measures. So we are trying to work around with this issue with a new method that we are developing, where we are trying to predict these secondary traits and later on introduce those as covariates in the model. But yeah, that's the most powerful way to improve predictability quite a lot. The way as it is, it works wonderful, and I think the integration with other omics like genomics will be very, very powerful in the future. I think we have traits that are very easy to collect. I mean, I'm not a specialist in this, but the canopy coverage, for example, using the drone data, at least in soybean, it shows a lot of potential, and probably it's not that complicated or that expensive to collect in fields other than uh, having to plant the genotypes in fields actually.
Okay, thank you. So we have more
Yeah.
questions.
Yeah, if I can just add to that, I mean, the planting of the genotypes is usually the most expensive. But I don't know about for you guys, but the harvesting with the combine is by far the most expensive part of all of that, because you've got to transport something that's big and dangerous and all of that. So with the phenomic prediction type methods, the goal, one of the things I can see is that you avoid potentially combining. You still may have to plant the individuals, but if you can avoid having to harvest them, that saves a bunch of effort.
Okay, thank you. So we have more questions. Yes, this question is from Jacqueline Schmitz. Great lecture, Dr. Yarkin. Are there any results for root traits to the different prediction methods in Ray et al. 2022? Is there a more appropriate method for analyzing nutritional stress tolerance?
Unfortunately, we didn't have access to root traits. So some of the issues sometimes that we face is, I mean, we develop the methods, the models, but we don't have access to the data types. So that would be interesting to try. Of course, if somebody in the audience have access to the data set and is happy or willing to collaborate, we can explore those things. Now, regarding the second question, if there are more appropriate methods for analyzing nutritional stress tolerance, I'm going to be honest, I never had a chance to work with these type of traits. I've been working with other similar traits, but we didn't find any specific way that is superior to another.
Okay, that's great. Thank you. So we have more questions. I think you don't have more questions. So for the finally, thank you so much, Dr. Seth and Dr. Diego. It was a pleasure to be you here, and I see you in the other in other moment. And have a great day. Okay.
Can I say something before we finish?
Yes. Yes. Free.
Yes. Sorry, I haven't announced this officially yet, but I'm looking for some students who might be who might have already trained in statistics, knows a little bit of phenomics, quantitative genetics, so ready to start as soon as possible in spring. So if you meet some of these characteristics, I will be more than happy reading your CV, your emails, your applications. And also I'm looking for 3 postdocs. So students and postdocs who are already trained for some of these areas, including a little bit of AI, are more than welcome to join my group.
Oh, that's great. It's to working in Colombia
No,
or
to Florida.
Florida.
University
Okay.
of Florida. Yes, in the
Okay.
agronomy
Oh,
department.
that's great.
So
And
we have
I can vouch Diego is one of the best and most cutting edge of the statisticians. So if you go work for him, you're almost guaranteed a great job by the time you graduate.
Oh, thank you, Seth. Very nice.
Okay. Okay. We have one more question here. It's from Charleston Lima. Among the vegetation index used, what are the best responses for plant biomass and senescence? I think it's from Dr. Seth.
Yes, it's for Seth.
Choose Seth, sorry.
Yeah, if I may have an answer for you here. I just went by the slide. Okay. If you would be so kind as to allow me to share my screen again.
Sure. Sure.
let's see if I can share screen one. All right, get that out of the way. Okay. So since you asked about biomass, I'll point out Shakira worked on biomass prediction from UAV and perennial sorghum. And so she found the RCC and BCC index were the most predictive. We've also used UAS now in cowpea, and I seem to remember BCC and RCC. And then also in maize grain, BCC and RCC tend to be some of the more predictive indices. But Charleston, the important thing to remember here is that it really takes no extra effort, or almost no extra effort, especially with that great package that Matthias developed, which I used at the beginning. I'm sorry, I can't remember the name off the top of my head. That Felipe Matias is a Brazilian as well, I believe.
Yes.
And now he's working at Syngenta, I think, but he just released a new package called Bison Fly.
Bison Fly, yes.
Yeah. Really important, great work. And with his package, you can extract all these vegetation indices at the same time. You know, and when I talk to my statistics colleagues here at Texas A&M, and I ask them why use so many different, neural network and random forest and all the different machine learning at the same time, they say, well, it's easy. You're not overfitting a model. You don't have to worry about overfitting by using them. And sometimes you discover important things. And so in the case of these vegetation indices, it's pretty easy to get them all and test them all at the same time. And so I wouldn't really worry about targeting a specific vegetation index because you're really looking for something that's predictive, I think, if you're a plant breeder. I don't know if that helps.
Okay, thank you, Dr. Seth. I think we don't have more questions. So I would like to thank you again, Dr. Seth and Dr. Diego. It was a nice day with great lectures and great discussions about the artificial intelligence and the other subject about that. Okay, so thank you again.
Thank you.
Okay. Thank you so much.
Bye.
Obrigado. Bye.
Bye. So we had now some information. Okay, guys, I invite the representative of GVENC, the study group from Universidade de São Paulo, Exalc, to announce the next event of the groups linked to the InterGen groups. Givanildo, hi. It's nice to having you here. The audience is yours. Feel free to present the event in Portuguese, no problem.
Hi, Jean. Do you can hear me?
Yes.
Oh, perfect. So I'm not practicing my English very much, but in the moment I will to speak in Portuguese for more confidence.
Okay.
So eu sou representante do GVENC até o momento, então participo do grupo do InterGen e represento o GVENC nesse grupo. Estamos com o próximo evento sendo o International Meeting and Plant Breeding. É o 6º nosso. Faço o convite a todos para estar participando de forma presencial com a gente. Então, ele ocorrerá no próximo dia 5, 6 e 7, de modo híbrido. As palestras, assim como as dúvidas, elas poderão ser feitas remotamente. Temos pesquisadores internacionais e também nacionais. Também temos 2 cursos a ser disponibilizados, a serem apresentados, lecionados nos dias 6 e 7, sendo um ofertado pelo professor Thiago Olivoto e o outro ofertado pelo Dr. Juan Pérez. Fiquem à vontade para estar participando e contamos com a presença de todos.
Beleza, Givanildo. Muito obrigado aí pelo seu anúncio aí. Eu tenho certeza que será um grande evento, assim, que ele vai contribuir muito aqui com os conhecimentos da área de genética e melhoramento de plantas. Bem, muito obrigado por sua participação aí, tá?
Eu que agradeço, Jean. Tudo de bom.
Para você também. Okay. So, guys, it was a great day with nice lectures and nice discussions about the genetics and plant breeding. But we have reached the end of our event. So, thank you to everyone who participated with us in these 3 days. So, the InterGen group appreciate the presence of all participants and speakers. We would like to thank the supporters, Corteva AgriScience, Rio Norte Sementes, Infoline Broadband, and the ConnectaGen group. We hope to meet all of you in the future events and share with you new experiences. So, a special thanks to the coordinators of InterGen 2022 and 2023 management. So I would like to thank you, Jaqueline Flores Schmitz, Bruna de Oliveira Duarte, Rosimara Barbosa Bispo, Luiz Gabriel Silva Alvarenga, Lorena Gabriela Coelho de Queiroz, Leonardo Oliveira Silva da Costa, Givanildo Rodrigues da Silva, Gabriel Henrique dos Santos Silva Salgado, Giovana Rodrigues Neves, Jéssica Argenta e João Marcos Soares. So guys, we will take a picture here to preserve this moment to the future. Okay?
Yes. So, galera, vamos falar em português agora. No 1, 2, 3, diga o X.
Todo mundo sorrindo, pessoal.
E outras pessoas tirem também, porque a minha câmera aqui pode falhar e eu posso não conseguir capturar a imagem boa. Então, tá bom? 1, 2, 3, X. Aqui foi. Mais alguém conseguiu capturar?
Foi.
Acho que sim.
Ok. Muito obrigada a todos que nos acompanhou durante esses 3 dias de evento. E foi um prazer estar com vocês e participar também dos minicursos. E ansiosos para o próximo ano.
Com certeza. Muito obrigado, pessoal.
Obrigada, pessoal.
Tenha uma ótima semana aí. Nos vemos no próximo evento, que é da Exalc. Tudo bem?
Tchau, tchau.
Tchau,
gente. Tchau.